I'm Dr. Chris Creighton, and we'll be discussing logarithmic and exponential equations. The core objective here is to solve equations using and involving exponential and logarithmic equations, and pretty much justifying your answer, so explaining how you got it and checking your solution. For our first example here, we'll be solving 5x is equal to 13. This is the biggest difference than before. So before, when we were solving exponential equations, we were able to write them in terms of the same base. But in this case here, we cannot. 5 and 13 are different bases. So like 5 is a prime, 13 is a prime. We can't write one in terms of the other one without the use of logarithms. So that's where the logarithms come in. So the first step here is to choose your base. You can choose any base you want. If you need to find a decimal value, then I would choose either log base 10 or natural log. So I'm going to try log base 10, so the common log. And what you would do is you take the logarithm of both sides. So log of 5 to the x is equal to log of 13. Now using properties of logarithms, this x pops down, so this is x log of 5 is equal to log of 13. So x is equal to log of 13 divided by log of 5. That is the solution to this equation here. And again, you can choose any base of logarithms you like. If you choose log base 5, this works out a little nicer. If you choose log base 13, there's another version of this. But the moral of the story is this same process will work for anything. I want to point out this is the exact answer, in that it doesn't have a truncated decimal, like you didn't round anything. The approximate answer, so to say to 3 decimal places, we would get log of 13 divided by log of 5, and that is 1.594. And this is an approximation. So if you need to know the answer to 3 decimal places, it's 1.594. But if I ask you for the exact solution, you would have to give me log of 13 divided by log of 5. So now let's take a look at this next example here. So we have e to the 0.0098x is equal to 28. Now this thing will have a solution as long as exponentials are equal to a positive number, because the range of exponential functions are 0 to infinity, not including 0. So in this case here, what we would do, again, is the same technique as above. Let's choose a logarithm. But this is e. Log base e is the natural log. So I'm going to choose the natural log for this one. So this is ln, if you would. And so if I take the natural log of both sides, this is e to the 0.0098x. And that's equal to log of 28. So now simplifying this side, we get 0.0098x log of e is equal to log of 28. And this is where choosing a nice logarithm works out. So we could have chose any base of logarithms for this, but what we see here is log of e. That's just 1. So that's equal to 0.0098x is equal to log of 28. So x is equal to log of 28, whatever value that is. You can punch that one into a calculator. Divided by 0.0098. This is the exact solution. And so for many of these, I will specify, give the exact solution. I do not want decimals. I want something written like this, involving logarithms. If you need a decimal approximation, at this point you can punch it into the calculator. On top of this, I just want to point out here, I chose the natural log because this has bases e. You could technically choose any base you would like. So now we're going to solve 3 to the x plus 2 is equal to 5 to the 2x plus 1. What's interesting about this one is that the bases are different, so we'll have to use logarithms, and we'll have to choose a logarithm. So for this one here, I'm going to choose log base 3 to show you how that one works. If you needed to know a decimal value, choose common log or natural log. If you choose another logarithm, like log base 3, in order to get an answer that you can evaluate, you would need to use change of base formula in the end. So again, it comes down to a choice here. So in this case here, I'm going to choose log base 3 because this actually works out pretty nicely if you choose these types of bases. So we get log base 3 of 3 to the x plus 2 is equal to log base 3 of 5 to the 2x plus 1. So in this case here, the exponents on both sides come down. So we get x plus 2 log base 3 of 3 is equal to 2x plus 1 times log base 3 of 5. And so log base 3 of 3, that's 1. This is very similar to choosing the natural log here. So now our goal is to get all the x's on one side and all of the things without an x on the other. So in this case here, we get an x plus 2 is equal to 2x log base 3 of 5 plus log base 3 of 5, distributing that in. So then we get an x minus 2x log base 3 of 5 is equal to log base 3 of 5 minus 2. So then factoring out this x, we get x is equal to log base 3 of 5 minus 2 divided by 1 minus 2 log base 3 of 5. This is our exact solution. If you need an approximation, you'll need to do a change of base on the log base 3 of 5s, and other than that, this is how you get an exact solution. Just be very careful going down here, so be careful. This is where I very often see algebra errors occurring. For instance, forgetting to distribute the log base 3 of 5 to that 1, or on the other side, if you chose a different base, distributing that logarithm, for instance. So just be careful for these. Now getting into the logarithmic side. So logarithmic side, your core goal here is to eventually convert it to exponential form. So in this case here, as written, we can just immediately convert this to exponential form. So I'll do that. So we get exponential form, which is 2x plus 8 is equal to 4 squared, which works out to 16. So we get 2x is equal to 8. So x is equal to 4. And for these ones here, for logarithmic equations, and this is going to be particularly true the second you start using properties of logarithms to solve logarithmic equations, is that you should get into a good habit of checking your answer. In this case here, this one's going to work. So if I do log base 4 of 2 times 4 plus 8, that is log base 4 of 16, and that is in fact 2 squared, so that one works. But the second you start using properties of logarithms, you're going to potentially run into issues with your solutions. You may get extras. So for our next one here, we have log base 6 of x squared plus 11 is equal to 2. Immediately able to convert that into exponential form. So we get x squared plus 11 is equal to 6 squared, which is equal to 36. So then x squared is equal to 25, which I do want to point out here, we get that there are two solutions. X is equal to 5, or x is equal to minus 5 here. So we have two solutions to this one. Just be very careful. Whenever you take the root, you're going to get x is equal to plus or minus square root of 25. So that's where the positive 5 and that's where the negative 5 comes from. So again, for this one, we have two solutions. That's because it comes from a quadratic. In this case, we do need to check our answers. So log base 6 of 5 squared plus 11, well, that's equal to log base 6 of 25 plus 11, which is 36, which is equal to 2. So that one works. And then doing the other one, log base 6 of minus 5 squared plus 11. That one's also equal to log base 6 of 36. That's a 6 up there, which is equal to 2. So they both are our two solutions there. With our last example here, I will solve this in two ways to show you the issue with using logarithmic properties. The first way I'll do is say this is a logarithm equaling a number. So the first thing we can do is convert this into exponential form to get x plus 1 squared is equal to 7 squared, which is 49. So then, taking the square root, we get x plus 1 is equal to plus or minus the square root of 49, which is equal to plus or minus 7. So in this case here, we get an x plus 1 is equal to 7, or x plus 1 is equal to minus 7, giving us the two solutions, x is equal to 6, or x is equal to minus 8. If you needed to check, which I'll not do that for both times, both work. So we actually have these two solutions here, which is great. But here's a big old warning. If you notice, using a property of logarithm, we can pull that 2 down. So this goes to 2 log base 7 of an x plus 1 is equal to 2. Dividing both sides by 2, we get log base 7 of an x plus 1 is equal to 1. Then converting that into exponential form, we get x plus 1 is equal to 7 to the 1. So then x is equal to just 6. We only get one solution. So what happened? Well, the big issue here is that we use the property of a logarithm. Properties of logarithms can either add or take away solutions. So in this case here, it took away the solution x is equal to minus 8. The reason being in that on the inside over here, this one has a larger domain. This one corresponds to x is strictly greater than negative 1. Or x is less than negative 1. You can't have x being negative 1 because that's log of 0. This one over here has a new domain restriction of x is only greater than negative 1, giving us only that 6 solution. So that property of a logarithm changed the domain of the function in such a way that it took away a solution. So in general, what you'll want to do is combine logarithms only. This adds solutions instead of removing. So expanding logarithms typically can remove solutions, while combining lobs will add solutions. And this is exactly why you must check your answer. And sometimes even with checking your answers, if you notice that property, that 2 coming down, you'll lost a solution, and checking your answer wouldn't do that. That 6 will work. It's just that you're missing the negative 8 due to the properties of logarithms. So in general, you will only want to combine your logarithms together into a single logarithm. That will add solutions. Then you must check your answers to make sure all of those solutions are in fact still solutions. And this is because the domains change when you use properties of logarithms.